Recently, scientists have come to believe that the exoplanets we previously identified as ocean planets might not actually have oceans, or even any water at all. The surfaces of these planets might be shrouded in thick layers of soot. These are referred to as soot planets by scientists. The term soot might sound unusual, reminiscent of the ash left after a fire, but in astronomical terms it refers to refractory organic carbon, a compound rich in carbon, hydrogen, oxygen, and nitrogen. Soot is quite prevalent in our solar system. It's estimated that 40% of a comet's total mass is made up of this material. What do these soot planets actually look like? And why were they mistaken for ocean planets? This matter begins with a large-scale statistical study of exoplanets. Currently, the number of confirmed exoplanets is nearing 6,000. Among these exoplanets, astronomers have discovered a very unusual type of planet. None of the 8 major planets in our solar system belong to this category, yet in the Milky Way beyond our solar system, these planets are quite common. They are neither small rocky planets like Earth nor gas giants like Jupiter, but rather a type that falls in between. These planets typically have a relatively low density, indicating they likely contain a significant amount of lightweight materials. They are larger than terrestrial planets, but smaller than Neptune, which is why astronomers refer to them as mini-Neptunes. It was once widely believed that these mini-Neptunes could be water worlds covered by vast oceans. Forming far from their stars allows them to absorb and store large quantities of water, eventually becoming ocean planets with rocky interiors enveloped by massive seas. This concept was very popular because it sparked a delightful imagination. The universe might be teeming with ocean planets, and there could even be a second Earth capable of supporting life. However, issues arose as observational technology and precision improved. Scientists discovered that the average density of many mini-Neptunes was not as low as the water world model had predicted. Furthermore, the water vapor content in their atmospheres was significantly different from expectations. Even more perplexing, the spectral characteristics of these planets are often unclear, as if obscured by a thick haze, which starkly contrasts with the clear atmospheric spectral features predicted by the water world model. Faced with various questions, scientists have considered a concept proposed in recent years, the soot line. You might be unfamiliar with the term soot line, but many people have heard of the snow line. Both are boundaries defined by temperature around a star. You could say these two lines respectively determine the two essential elements for carbon-based life, water and carbon. The snow line marks the boundary in a star disk where water ice can stably exist at a temperature of about 160 Kelvin, which is around minus 113 degrees Celsius. Inside the snow line, the temperature is too high, causing water ice to easily sublimate into gas. Only outside the snow line can water ice stably exist. The soot line, however, is closer to the star than the snow line. It defines the boundary in a star disk where carbonaceous organic particles can stably exist at a temperature of about 500 Kelvin, which is 227 degrees Celsius. Inside the soot line, high temperatures decompose carbonaceous organic particles, and only outside can these particles be preserved. Therefore, the protoplanetary disk is divided into 3 regions by these 2 lines, and each region gives rise to different types of planets. For instance, inside the soot line closest to the star, the high temperature prevents soot from accumulating, leading to the formation of terrestrial planets. These rocky planets are considered to be lacking both water and carbon. Indeed, even though 2/3 of Earth's surface is covered by oceans, it is still regarded as a water-deficient planet. Additionally, Earth is carbon poor, with only 0.024% carbon content in the crust. Given this, the evolution of carbon-based life on a planet like Earth, which is not abundant in water or carbon, is truly remarkable. Between the soot line and the snow line, although water cannot be retained due to high temperatures, carbon can be preserved in large quantities. Planets formed here are typically water-deficient but carbon-rich, marking the birthplace of soot planets. Beyond the snow line, despite the low temperature, planets usually have both water and are carbon-rich. These planets can also be referred to as soot water planets, which is why they are sometimes mistaken for ocean planets. Because of the presence of soot water, the average density of many mini-Neptunes is about the same as that of water, but slightly higher. At this point, someone might wonder why there aren't any soot planets or soot water planets in the solar system. Hey, why isn't there anything? We've mentioned that about 40% of comets could be made up of soot, which means they are essentially mini soot water planets. As for why there aren't larger planets, it's mainly due to the relatively low carbon content in the primordial solar system disk, along with factors such as the efficiency of planet formation, which ultimately prevented the formation of a particularly large soot-water planet in the solar system. What would ash planets be like if they truly existed? Scientists have simulated the internal structure of such planets. The results show that even if ash makes up only 0.1% to 1% of the planet's total mass, the carbon content in the mantle would still be substantial. As the planet cools, geochemical reactions would gradually release carbon from the mantle into the atmosphere, manifesting as gases like methane, acetaldehyde, and ethylene. Under the ultraviolet radiation from the star, these small molecules would recombine to form more complex hydrocarbon chains. These chains would then condense into tiny particles, creating a smog-like haze. Over billions of years, the entire planet would be enveloped in this thick organic haze, with sunlight barely penetrating to the surface. Whether day or night, the ground would remain in complete darkness. This explains why the atmospheric spectra of many mini-Neptunes appear blurry, not due to inadequate equipment, but because the haze is so dense that it obscures the signals. The surface of such planets inevitably brings to mind Titan, Saturn's moon. As the second largest moon in the solar system, Titan is even larger than Mercury. Its distance from the Sun results in extremely low surface temperatures, causing water on Titan to exist only as ice. Similar to ash-water planets, Titan also contains a substantial amount of carbon. Its surface is similarly covered by organic haze, such as methane smog. Additionally, its surface features lakes and seas composed of liquid methane, ethane, and some more complex hydrocarbon compounds. In a sense, Titan is a miniature version of those ash-water planets, albeit with a less complex and extreme environment. Not only is the surface peculiar, but the mantles of these planets are also unusual. Due to the massive carbon presence under the high temperature and pressure inside the planet, the carbon in the mantle likely transforms into substances like graphite and diamond. That's right, these planets might be filled with diamonds inside. So diamonds really aren't rare at all. Compared to gold, which can only be formed by supernova explosions or neutron-star collisions, the diamonds produced inside planets are hardly worth mentioning. Moreover, this diamond mantle poses many drawbacks for life. It would alter the planet's heat conduction method, suppressing plate tectonics and hindering the generation of the planet's magnetic field, leaving the surface vulnerable to stellar wind erosion. At first glance, such an environment seems lifeless, almost a forbidden zone for life. However, upon deeper study, scientists have discovered that although the atmospheres of these planets are murky, they resemble a natural chemical factory. Ultraviolet light continuously drives the reactions of hydrocarbons, constantly generating complex organic molecules. It's crucial to understand that when these organic molecules encounter water, they can form simple amino acids. This implies that for ash-water planets with a certain amount of water, the simultaneous presence of carbon and water, these two key elements, makes the emergence of life not entirely impossible. The detection of exoplanets and signs of life is one of the main tasks of the Webb telescope. In recent years, its observational results have also supported the ash-water planet hypothesis to a certain extent. For instance, it has found that the atmospheres of some mini-Neptunes indeed exhibit abnormally high carbon content. Even through transmission spectroscopy, traces of methane, carbon dioxide, and water vapor have been detected in the planet's atmosphere. All of these are consistent with the model of ash-water planets. If future observations can continue to confirm the correctness of this model, it would also suggest that compared to the vibrant blue planets, the lifeless black worlds might be more common in the universe. But who can guarantee that in that pitch black world, there wouldn't exist other forms of life completely different from Earth's?